The Milky Way is our magnificent cosmic home, a vast spinning island of stars, planets, dust, and dark matter, stretching about 100,000 light-years across. From its glowing spiral arms to the mysterious black hole at its heart, the Milky Way is both familiar and full of secrets. In this video, we'll uncover 100 fascinating facts about the Milky Way. So, watch this video till the end and subscribe to the channel. Let's begin. Deep in the heart of the Milky Way lies a monster that bends both time and space itself, a supermassive black hole known as Sagittarius A. Hidden behind dense clouds of gas and dust, it sits roughly 27,000 light-years away from Earth in the constellation Sagittarius, anchoring the galaxy with its immense gravity. This cosmic giant is about 4 million times more massive than our Sun, yet it's confined to a region no larger than our solar system. Around it, stars race through the darkness at unimaginable speeds, caught in its gravitational grip. One of these stars, called S2, completes an entire orbit around Sagittarius A every 16 years, moving at speeds of over 7,600 kilometers per second. A breathtaking cosmic ballet that confirms the black hole's immense pull. For decades, Sagittarius A was invisible, detectable only through the way it influenced nearby stars and gas. But in 2022, humanity finally captured its image, thanks to the Event Horizon Telescope, a global network of radio observatories that worked together to photograph the faint, glowing ring of gas swirling around the black hole's shadow. It was a defining moment in astronomy, proof that the mysterious heart of our galaxy was real, and that we could finally glimpse the very edge of physics itself. Yet Sagittarius A may not be alone. Astronomers believe the Milky Way could harbor tens of millions of smaller black holes scattered throughout its disk and halo, remnants of ancient, dead stars. Some might roam unseen, drifting silently through interstellar space, while others could lurk near star clusters or within the galaxy's outskirts. These hidden black holes are nearly impossible to detect directly, but their presence can sometimes be inferred when they distort light or tug subtly on nearby stars. Together, these massive and miniature gravitational wells shape the Milky Way's structure, influence star formation, and even affect how our galaxy evolves over time. Just beyond the mysterious heart of Sagittarius A, the Milky Way reveals itself as a magnificent barred spiral galaxy, a celestial masterpiece shaped by gravity and time. Unlike simple spiral galaxies with neat, uniform arms, ours has a bright central bar made of densely packed stars stretching across its core. This bar acts almost like a galactic highway, funneling gas and dust inward toward the center, fueling star formation and feeding the supermassive black hole that anchors it all. From this glowing bar extend 4 vast, winding arms: Perseus, Scutum Centaurus, Sagittarius, and Norma, each a river of stars, nebulae, and cosmic clouds swirling around the core like luminous ribbons in space. Tucked quietly between the grand arms lies a smaller, lesser-known spur called the Local Arm, or Orion Arm, a modest structure just a few thousand light-years wide. This is our neighborhood, the region of the galaxy that the Sun and its planets call home. From here, when we gaze up on a clear, dark night and see the Milky Way stretched like a pale band across the sky, we're actually looking along the plane of this very arm, peering through billions of stars that share our galactic orbit. Yet the Milky Way isn't the perfect flat disk that early astronomers once imagined. In reality, it's warped, bent and twisted like a giant cosmic potato chip. The edges of the disk curve upward and downward, likely due to the gravitational influence of nearby galaxies and the mysterious halo of dark matter that envelops it. And this grand spiral structure doesn't sit still. The entire galaxy is in motion, rotating once every 230 million years, meaning the last time the Sun was in this same position, dinosaurs roamed the Earth. Every star, planet, and dust cloud is part of this vast rotating dance, turning in harmony around the galactic center in an endless cycle of creation and change. Drifting outward from the elegant spiral structure of our galaxy, we find ourselves among one of the most mesmerizing truths of the cosmos. The Milky Way is a sea of stars so immense, so densely populated, that the human mind can scarcely comprehend its scale. Astronomers estimate that our galaxy contains between 200 and 400 billion stars, and some estimates even stretch that number to 500 billion when accounting for the faintest, most elusive ones hidden in the galactic outskirts. Every single point of light we see in the night sky belongs to just a tiny portion of this grand stellar ocean, and yet we've only begun to scratch the surface of what truly lies within it. Despite the overwhelming abundance of stars, most of them are far smaller and dimmer than our Sun. In fact, nearly 3/4 of all stars in the Milky Way are red dwarfs, tiny, cool, and faint stars that burn their fuel so slowly that they can live for trillions of years, far longer than the universe's current age of about 13.8 billion years. These humble red stars make up the silent majority of the galaxy's population, invisible to the naked eye, yet essential to its balance. If the Milky Way were a city, red dwarfs would be its quiet residents, numerous, enduring, and scattered everywhere, forming the steady heartbeat of the galactic community. Then there are the yellow dwarfs, stars like our Sun, moderate in size and brightness, stable for billions of years, and capable of nurturing life on orbiting planets. They make up only a small fraction of the total stellar count, yet they play an outsized role in shaping planetary systems and perhaps civilizations. Our own Sun is a fairly ordinary example of this group, just one among hundreds of billions of stars that share the same cosmic stage. At the far extreme of the stellar spectrum lie the blue giants, massive, luminous, and rare. These are the short-lived celebrities of the galaxy, burning through their nuclear fuel in only a few million years before ending in spectacular supernova explosions that seed the galaxy with heavier elements. Though they make up less than 1% of all stars, their impact is enormous. They illuminate nebulae, sculpt interstellar gas clouds with their intense radiation, and forge the very carbon, oxygen, and iron that make life possible. Some of the brightest stars we can see from Earth, like Rigel or Deneb, are members of this rare, radiant class. The distribution of stars across the Milky Way reveals much about its history and evolution. The galaxy's spiral arms, those graceful glowing bands that stretch outward from the central bar, are its stellar nurseries. Within them, massive clouds of gas and dust collapse under gravity to form new stars, often in clusters. Here, we find the twinkling brilliance of newborn suns surrounded by protoplanetary disks, the faint blue shimmer of star-forming regions, and the violent winds of supernova remnants. These arms are the galaxy's creative zones, continually renewing themselves over billions of years. Closer to the galactic center, however, the story changes. This region, known as the bulge, is densely packed with older, redder stars, veterans of ancient generations that formed when the galaxy itself was young. Many of these stars are billions of years old, remnants of a time when the Milky Way was still assembling itself through cosmic mergers and collisions. Beyond the visible disk lies the halo, a vast and faint sphere that surrounds the galaxy, home to some of the oldest known stars and clusters, stellar fossils left behind from the galaxy's earliest days. These ancient halo stars are low in heavy elements, meaning they were born before the universe had been enriched by repeated cycles of stellar death and rebirth. But for all our telescopes, satellites, and surveys, counting the stars in the Milky Way remains one of astronomy's greatest challenges. The problem isn't just distance, it's dust. Thick clouds of interstellar dust fill the galactic plane, especially along the spiral arms, absorbing and scattering visible light. To our eyes, this creates dark patches and lanes that obscure much of the galaxy's true population. Even the most powerful optical telescopes cannot penetrate these dense regions, leaving vast numbers of stars hidden from view. To overcome this, astronomers use infrared and radio telescopes, which can see through the dust and reveal the stars beyond. The European Space Agency's Gaia spacecraft, for instance, is mapping the precise positions and motions of over 1 billion stars, helping us construct the most detailed 3D model of our galaxy ever created. Even so, Gaia's data represents only a small fraction of the total number. Many dim red dwarfs, distant giants, and stars buried deep in the galactic bulge remain unseen, reminding us that much of our own home galaxy is still cloaked in mystery. Another complication comes from binary and multiple star systems, which are more common than solitary stars like our Sun. In fact, about half of all stars are thought to exist in pairs or groups, orbiting around a common center of mass. This makes accurate counting even harder, since what appears as one faint point of light could actually be several stars bound together by gravity. So while we estimate hundreds of billions of stars in our galaxy, that number could easily be off by tens of billions either way. What's certain, though, is that every one of those stars contributes to the Milky Way's brilliance. Each a sun with its own potential worlds, its own history, and its own role in the grand cosmic web. When you look up at the night sky, you're not just seeing a random scattering of lights. You're gazing into a cross-section of an enormous, living system that has been forming and reforming for over 13 billion years. And yet, even with all our knowledge, the act of counting stars reminds us how small we truly are. The Milky Way's dust clouds hide more than light. They hide the limits of human perception, the boundaries of what we can currently know. Beyond them lies the rest of the galaxy, waiting patiently for us to find new ways to uncover its secrets. Although the Milky Way dazzles us as a glowing band across the night sky, what we see is only a fraction of its true majesty. Much of our galaxy is hidden from human eyes, veiled behind enormous clouds of interstellar dust, tiny particles of carbon, silicates, and ice that drift between the stars. These microscopic grains, formed from the remnants of long-dead stars, scatter and absorb visible light, turning the Milky Way into a patchwork of bright and dark regions when seen through an optical telescope. To our unaided eyes, this dust creates the dark rifts and streaks that slice through the luminous disk, giving the galaxy its textured appearance. But behind these obscuring curtains lies an invisible cosmos, a realm of starbirth, turbulent gas, and blazing energy that ordinary vision cannot perceive. Interstellar dust may sound insignificant, but its impact on what we see and don't see is immense. Each dust grain is smaller than a speck of smoke, yet collectively they form vast dust lanes that stretch for thousands of light years across the galaxy's spiral arms. These lanes act like cosmic blinds, blocking visible starlight and hiding much of the Milky Way's true population. If you could somehow strip away all this dust, the night sky would be unrecognizably bright, crowded with stars so dense that darkness itself would nearly disappear. But the dust doesn't just obscure, it also gives birth. Within these cold, dark regions, gravity pulls gas and dust together to form stellar nurseries, where new stars ignite from collapsing clouds of hydrogen. In a sense, the dust that hides the Milky Way's light is also the very substance that sustains its life cycle. Since visible light cannot penetrate these dense veils, astronomers turn to other forms of light, infrared and radio waves, to uncover what's hidden. Infrared telescopes, such as NASA's Spitzer Space Telescope and the James Webb Space Telescope, can peer straight through dusty regions that appear opaque in optical wavelengths. In infrared light, the Milky Way reveals a different face: filaments of glowing gas, clusters of newborn stars, and intricate webs of dust illuminated from within. Similarly, radio telescopes can detect emissions from neutral hydrogen, the most abundant element in the universe, mapping the structure of the galaxy even where light cannot reach. Through these technologies, astronomers have discovered immense, previously invisible regions of the Milky Way, filled with star-forming activity and complex dynamics that define its evolution. One of the most extraordinary areas revealed by these observations lies in the direction of the galactic center, toward the constellation Sagittarius. To the naked eye, this region appears as a murky patch of sky with little visible detail. But in reality, it's the heart of the Milky Way, where billions of stars are packed into a region only a few thousand light-years across. It's an environment so crowded that stars can be just a fraction of a light-year apart, compared to the 4 light-years separating our Sun from its nearest neighbor, Proxima Centauri. Yet, because of the thick layers of dust and gas that lie between us and the center, this teeming region remains mostly hidden in visible light. Only through infrared and radio imaging can we witness the dazzling heart of our galaxy, the glowing central bulge, the swirling gas clouds orbiting Sagittarius A, and the intricate structures sculpted by gravity and stellar winds. Within these dusty realms, we find some of the most breathtaking sights in the Milky Way. Massive molecular clouds stretching hundreds of light-years wide, filled with the raw materials for star formation. Regions such as the Eagle Nebula, Orion Nebula, and Carina Nebula are just small glimpses into this hidden architecture. In visible light, they appear as faint, cloudy patches. But in infrared, they come alive with color and motion, revealing clusters of young stars still wrapped in their dusty cocoons, and shockwaves from newly formed suns carving cavities through their birth clouds. The interplay of light and shadow within these regions gives the galaxy its dynamic texture, as if it were breathing through cycles of obscurity and illumination. Even our own view of the Milky Way from Earth is shaped by this interstellar dust. When we gaze up at the night sky from a dark location, the glowing band we call the Milky Way is actually our edge-on view through the galactic disk. The bright patches are areas where starlight escapes relatively unblocked, while the dark gaps mark dense concentrations of dust. For centuries, these dark regions puzzled observers. Ancient astronomers saw them as rips in the heavens or celestial rivers of smoke. It wasn't until the 20th century that scientists realized these were dust clouds, massive structures that obscure millions of stars lying beyond them. The irony is that without dust, the Milky Way might not look like the Milky Way at all. Those dark, sinuous streaks slicing through the galactic plane give the galaxy its personality, hinting at the powerful forces at work within. And while they obscure much of the visible light, they also re-radiate energy in infrared wavelengths, creating a subtle, diffuse glow that infrared telescopes can detect. This emission helps scientists map the distribution of dust itself, allowing us to understand where new stars are likely to form and how the galaxy's spiral structure evolves over time. Moreover, interstellar dust plays a crucial role in chemistry and planet formation. Dust grains serve as cosmic laboratories, where atoms stick together and form molecules: water, carbon dioxide, methane, and even complex organic compounds. When new stars form, this material becomes part of the protoplanetary disks that eventually birth planets, moons, and asteroids. In other words, the same dust that hides the Milky Way's light is also the source of everything solid we know: rocks, worlds, and even life itself. So the next time you look at the Milky Way on a clear, moonless night, know that what you see is only the surface of something far grander. Beyond those dusty shadows lies a galaxy alive with hidden light, stars in the making, and secrets still waiting to be uncovered. The dust both conceals and creates. It hides the galaxy's face, but whispers its story through other wavelengths. In the dark lanes and invisible depths of the Milky Way lies the dual nature of the cosmos itself. Mystery and revelation, silence and creation, death and rebirth intertwined in the most beautiful of ways. As we move away from the glowing heart of the Milky Way and drift outward into its vast spiral disk, we find ourselves in a calm and relatively peaceful corner of the galaxy, a cosmic suburb, far from the violent chaos of the galactic center. Our solar system lies about 27,000 light-years from that central bulge, situated in one of the quieter regions between two of the Milky Way's major spiral arms, the Sagittarius arm and the Perseus arm. This tranquil zone is part of a smaller spur called the local arm, or Orion arm, a modest bridge of stars and gas stretching a few thousand light-years across. It's not one of the galaxy's grand spiral highways, but rather a cozy side street, an unassuming neighborhood where the sun and its planets orbit in relative peace, undisturbed by the galaxy's more turbulent regions. This location is no accident of cosmic chance. It's one of the reasons life may have been able to thrive here. Closer to the galactic center, the density of stars increases dramatically, along with the frequency of supernovae, gamma-ray bursts, and other high-energy events that can sterilize entire regions of space. Farther out, beyond the main disk, there is too little material for star and planet formation to be common. But here, in the mid-range of the galactic disk, conditions are just right. Enough heavy elements to build rocky planets and stable orbits, but distant enough from extreme cosmic violence to allow billions of years of evolution. Our Sun, therefore, occupies not only a stable orbit, it sits in what astronomers sometimes call the galactic habitable zone. Orbiting the Milky Way's center is a grand journey in itself. The entire solar system travels around the galaxy at a breathtaking 828,000 kilometers per hour. That's about 230 kilometers per second. Even at that incredible speed, one full orbit takes roughly 230 million years. This means that since the Sun was born, about 4.6 billion years ago, it has completed only around 20 full revolutions around the galactic center. In that time, the face of Earth has changed completely. Continents have shifted, species have risen and fallen, and civilizations have appeared and disappeared. All while we slowly glide through the galaxy's spiral arms in a vast cosmic dance we barely notice from our vantage point. But our solar system doesn't drift alone through this great cosmic sea. The Milky Way is surrounded by an entourage of smaller companions, about 50 known satellite galaxies, each orbiting within the gravitational embrace of our galactic giant. These dwarf galaxies come in many forms. Some are diffuse and faint, while others are compact and dense. Two of the most famous are the Large and Small Magellanic Clouds, visible from the southern hemisphere as hazy patches of light. These two irregular galaxies are among our nearest neighbors, lying roughly 160,000 and 200,000 light-years away, respectively. They orbit the Milky Way like loyal companions, though their orbits are anything but simple. Gravitational tides from our galaxy are slowly distorting and stripping them of stars and gas. In fact, streams of material, known as the Magellanic Stream trail behind them, stretching across a vast arc of the sky, evidence of their long and complex gravitational relationship with the Milky Way. Beyond these two bright companions are dozens of faint dwarf spheroidal galaxies, such as the Sagittarius dwarf galaxy, Ursa Minor dwarf, and Draco dwarf, each containing only a few million stars, mere fragments compared to the hundreds of billions in our own galaxy. These small systems are relics of galactic evolution, survivors of an ancient process called galactic cannibalism, where larger galaxies grow by absorbing smaller ones. Indeed, the Milky Way has been devouring its neighbors for billions of years, and these satellite galaxies represent both its past victims and future meals. Some of their stars have already been pulled into long, looping stellar streams that wrap around our galaxy like cosmic fingerprints, tracing the invisible contours of its gravitational field. All of this cosmic structure, our Sun's suburban orbit, the satellites surrounding us, and the larger galaxies beyond, exists within a much greater framework known as the local group. This small cluster of about 80 galaxies spans more than 10 million light-years across and is bound together by mutual gravity. The Milky Way is one of the two dominant members of this group, the other being the Andromeda galaxy, M31, our massive sister galaxy, located about 2.5 million light-years away. Andromeda is slightly larger than the Milky Way, and, intriguingly, the two are currently moving toward each other at about 110 kilometers per second, a slow but inevitable approach that will culminate in a colossal merger billions of years from now. Alongside these two galactic titans are smaller members such as the Triangulum galaxy, M33, a beautiful spiral that may be gravitationally bound to Andromeda, and numerous dwarf companions like Leo I Fornax and Carina. Together, these galaxies orbit a shared gravitational center somewhere between the Milky Way and Andromeda, drifting collectively through the cosmic web like a small flotilla amid the vast dark sea of intergalactic space. If you could look at the Milky Way from far above its disk, you would see these satellites and companions like a swarm of fireflies surrounding a great glowing wheel. The view would be both humbling and inspiring, a reminder that our galaxy, massive as it is still only one island in a vast archipelago of galaxies extending beyond human imagination. The local group itself is just one cluster among countless others, each containing its own spirals, ellipticals, and irregulars, all bound by the grand structure of the cosmic web. So here we are, orbiting quietly in the local arm of a spiral galaxy, nestled in a small group of companions, circling through an expanding universe that stretches far beyond our comprehension. From the heart of the Milky Way to the farthest dwarf galaxy in its halo, everything is connected through gravity's silent pull. Our solar system may be a speck in this grand structure, but it's a privileged one, perfectly placed in a calm, stable corner of an extraordinary galaxy, surrounded by a neighborhood that is as ancient as time itself. From our peaceful corner of the Milky Way, if we were to look closely at the galaxy's luminous arms and glowing nebulae, we would see that the Milky Way is not static, it's alive. Every moment within its grand spirals, stars are born, live brilliant lives, and die spectacular deaths, fueling an endless cycle of creation and destruction that defines the galaxy's very essence. The story of the Milky Way is, in many ways, the story of its stars, their births in clouds of dust, their luminous youth, their fiery ends, and their quiet transformation into the building blocks of new generations of worlds. It all begins in the nebulae, vast clouds of gas and dust scattered throughout the galaxy. These nebulae are the cradles of stars, enormous molecular clouds made mostly of hydrogen and helium, the same elements forged in the Big Bang. Over time, gravity pulls denser regions of these clouds inward, causing them to collapse and heat up. As pressure builds, the central core ignites nuclear fusion, converting hydrogen into helium and releasing immense energy. In that moment, a new star is born, pushing away the surrounding gas with stellar winds and lighting up the nebula like a cosmic lantern. These star-forming regions, such as the Orion Nebula or the Eagle Nebula's pillars of creation, are among the most beautiful structures in the Milky Way, shimmering with the glow of newborn suns. Once a star has formed, its life depends primarily on its mass. Small stars, like red dwarfs, burn their fuel slowly, glowing dimly for trillions of years, far longer than the universe has existed so far. Medium-sized stars, like our Sun, live steady lives for billions of years, maintaining a delicate balance between the inward pull of gravity and the outward pressure of fusion. Massive stars, however, live fast and die young. They burn through their nuclear fuel in only a few million years, shining with incredible brightness before collapsing in violent supernova explosions that outshine entire galaxies for a brief, dazzling moment. Supernovas are not just magnificent displays, they are cosmic forges, where the universe's heavier elements are created. Inside these dying giants, nuclear fusion creates elements up to iron, but when they explode, the extreme temperatures and pressures allow even heavier elements to form: gold, silver, uranium, and more. These materials are scattered across the galaxy, enriching the interstellar medium with the raw ingredients for planets, moons, and eventually, life. Every atom of carbon in our bodies, every bit of iron in our blood, and every molecule of oxygen we breathe was once created in the heart of a star and released into space by a stellar death. As the astronomer Carl Sagan famously said, "We are made of star stuff," a truth that connects every human being directly to the Milky Way's stellar past. After a supernova, the remains of the star can take several forms depending on its mass. A medium-sized star like the Sun ends its life by shedding its outer layers, forming a glowing planetary nebula around a small, dense core called a white dwarf, a hot ember that will slowly cool over billions of years. A massive star, however, undergoes a much more violent transformation. Its core collapses under gravity, forming a neutron star, an incredibly dense object with the mass of the Sun packed into a sphere just a few kilometers wide. Or, if the star is even more massive, a black hole, from which nothing, not even light, can escape. These remnants then become part of the galaxy's hidden population, influencing nearby stars and gas through their immense gravity and high-energy radiation. The material expelled by dying stars, gas, dust, and elements heavier than helium, mixes with the interstellar medium, enriching it and setting the stage for new generations of stars. Over billions of years, this galactic recycling process has made each new wave of stars and planets more chemically complex than the last. The first stars, which formed just after the Big Bang, were made almost entirely of hydrogen and helium. Today's stars, however, contain traces of carbon, oxygen, silicon, and iron, elements born in countless ancient explosions. This progressive enrichment is why planets like Earth, with its iron core and complex chemistry, can even exist at all. In this cosmic life cycle, the Milky Way functions like a living organism, constantly consuming, transforming, and renewing itself. Star birth and death are not random events, but interconnected phases of an ongoing process that spans billions of years. Every glowing nebula in the sky is a nursery where new stars are taking shape from the ashes of older ones. Every cluster of bright young stars represents the latest chapter in a story that began long before our solar system existed, and every dark, dusty region in the galaxy may one day give birth to new worlds and, perhaps, new life. Some of the oldest stars in the Milky Way, and even beyond, carry evidence of this ancient history. A few stars have been discovered that are so old they may predate the galaxy itself. One of them, the Methuselah star, HD 140283, is estimated to be about 14 billion years old, nearly as old as the universe. These ancient stars are like fossils, remnants of the earliest stellar generations that formed shortly after the Big Bang, its own. Their existence proves that the Milky Way was built from smaller, primitive galaxies that merged together, bringing with them these ancient lights from the dawn of time. When we look up at the night sky, we are witnessing stars at every stage of this immense cycle, some just forming, others in their prime, and many nearing their end. In this grand tapestry, our Sun is merely a middle-aged star, about 4.6 billion years into its roughly 10 billion year lifespan. One day, it too will expand into a red giant, engulfing the inner planets before shedding its outer layers and leaving behind a glowing white dwarf surrounded by a delicate planetary nebula. The elements from our Sun will then drift into space, perhaps one day becoming part of another star, another planet, or even another form of life. Thus, the Milky Way is not just a collection of stars, it's a cosmic ecosystem where nothing truly dies, but everything transforms. The stars live and die to create new generations, enriching the galaxy and perpetuating an endless cycle of rebirth. Each point of light in the sky is not just a star. It's a story in motion, a chapter in a grand saga of creation that stretches back to the dawn of the universe and will continue long after we are gone. Long before the Milky Way took on its graceful spiral form, before the Sun, Earth, or even our corner of the cosmos existed, there were ancient stars, faint, enduring lights that have burned since the earliest chapters of the universe. These primordial stars are among the most precious relics in astronomy, the living fossils of our galaxy's deep past. Scattered across the Milky Way, they tell a story older than the galaxy itself, a story of cosmic birth, survival, and transformation that began mere hundreds of millions of years after the Big Bang. One of the most remarkable of these ancient survivors is HD 140283, more poetically known as the Methuselah star. Named after the biblical figure, reputed to have lived nearly 1,000 years, this star's age is so immense it almost defies logic. Around 14 billion years old, give or take a margin of uncertainty. That's nearly as old as the universe itself, which is estimated to be 13.8 billion years old. Located about 190 light-years away in the constellation Libra, the Methuselah star is a subgiant, meaning it's nearing the end of its life and beginning to exhaust its hydrogen fuel. It burns faintly, quietly, and with an extraordinary history written in its very chemistry. The Methuselah star is what astronomers call a population 2 star, part of the second generation of stars ever formed. Its atmosphere is almost devoid of heavy elements, what astronomers call metals, a telltale sign that it was born before supernovas had enriched the cosmos with the ingredients for planets and complex chemistry. In its simplicity, HD 140283 carries the chemical fingerprint of an early universe composed almost entirely of hydrogen and helium, with only faint traces of lithium. When astronomers study its light, they are peering directly into a time when the cosmos was young and raw, before galaxies had matured or heavy elements had become widespread. But HD 140283 is not alone. Throughout the Milky Way's halo, far beyond the luminous spiral arms, lie other ancient stars, some nearly as old, all belonging to the galaxy's earliest generations. These stars formed from the gas clouds that collapsed soon after the universe's first explosions, possibly within the small proto-galaxies that merged to form the Milky Way billions of years ago. Their orbits are long and elliptical, cutting through the galactic disk at steep angles, tracing the remnants of those early mergers. Each of these stars is a messenger from the beginning, a relic of the galaxy's chaotic birth. Even more spectacular than individual ancient stars, are the vast globular clusters that orbit the Milky Way like glowing, time-worn jewels. These clusters, spherical gatherings of hundreds of thousands, sometimes millions of stars, are among the oldest structures in the entire universe, many of them dating back 12 to 13 billion years. Each cluster is a densely packed ball of ancient suns, bound tightly together by gravity and moving through space as a single unit. From a distance, they appear as faint, fuzzy points of light, but through a telescope, they explode into dazzling swarms of golden stars, shining like cosmic chandeliers against the black velvet of space. One of the most famous examples is Omega Centauri, a breathtaking globular cluster visible to the naked eye from the southern hemisphere. Containing roughly 10 million stars, it is so large and massive that astronomers suspect it might once have been the core of a small galaxy devoured by the Milky Way long ago. Another, M13, the Great Hercules Cluster, dazzles observers with its dense, shimmering core. Over 300,000 stars packed within a region only 145 light-years across. To stand under a dark sky and glimpse these ancient clusters is to look directly into the Milky Way's fossil record, into the light of stars that have burned since long before our world was born. These globular clusters are more than beautiful. They are essential to understanding the Milky Way's formation. Their age, chemical composition, and orbital paths reveal how the galaxy grew over billions of years. Most of them orbit far outside the galactic disk, within the Milky Way's halo, following long, looping trajectories that sometimes bring them close to the center, before swinging them far into intergalactic space. Their wide distribution suggests that they are remnants of the early building blocks that merged to form our galaxy, perhaps the shattered cores of ancient galaxies or the first clumps of matter to collapse after the Big Bang. Each cluster tells a slightly different version of the same story. Some are rich in stars with slightly higher metallicities, meaning they formed a bit later, after earlier generations of stars had already seeded the cosmos with heavier elements. Others are extremely metal-poor, suggesting they were born in the universe's youth, when hydrogen and helium were nearly all that existed. Together, they form a cosmic archive, a record of how the Milky Way grew through hierarchical merging, absorbing smaller galaxies and incorporating their stars and clusters into its own vast system. In a sense, the Milky Way's oldest stars and globular clusters are archaeological relics of the universe. They provide clues about the conditions that prevailed when the first galaxies were forming and the first stars began to shine. Their compositions help astronomers determine how fast the universe enriched itself with heavy elements, how the first supernovas spread their metals, and how galaxies evolved from small, irregular blobs into the grand spirals and ellipticals we see today. But these ancient stars also carry a deeper, more poetic significance. They remind us of how ancient our origins truly are. The atoms that make up our bodies were once part of the same universe that gave birth to HD 140283 and the stars of Omega Centauri. The light from these old suns began its journey across space long before the Earth formed, before the Sun ignited, before the Milky Way even reached its modern shape. And yet, they still shine, quietly defying the vastness of time. If the Milky Way were a living being, these ancient stars would be its memory, traces of its childhood preserved in the night sky. They orbit far from the bustling galactic disk, untouched by the chaos of modern star formation, silently circling as witnesses to cosmic history. Each one is a chapter from the universe's oldest story, written in light that has traveled for billions of years to reach our eyes. When astronomers gaze upon them, they are not just studying stars. They are looking back to the very dawn of creation, to the first sparks that lit the darkness after the Big Bang. These ancient suns, steadfast and enduring, remind us that the Milky Way's history is written across the ages in layers of starlight. From the Methuselah star to the distant globular clusters, the galaxy carries its past with it, etched into its halo, whispering through its light and waiting for us to listen. Among the billions of stars that populate the Milky Way, not all wander alone. Many are born and live their early lives in great cosmic communities known as star clusters, gravitationally bound families of stars that share a common origin. These clusters are the stellar cities of the galaxy, places where stars are born together from the same cloud of gas and dust, shining side by side before drifting apart or remaining bound for billions of years. They come in two main forms, open clusters and globular clusters. And though they share the same fundamental nature, their differences reveal two very distinct eras in the history of the Milky Way. Open clusters are the younger, more vibrant neighborhoods of the galaxy. Found primarily in the Milky Way's spiral arms and disk, these clusters form within the vast molecular clouds that stretch across the galaxy's plane. They typically contain anywhere from a few dozen to a few thousand stars, all born from the same collapsing cloud of gas. Because they are relatively young, usually a few million to a few 100 million years old, their members often include hot, bright blue stars that illuminate the surrounding gas and dust. These youthful clusters are like cosmic nurseries, bustling with activity and light, but destined to disperse over time as their stars drift apart under the influence of gravity and galactic tides. One of the most famous open clusters is the Pleiades, also known as the Seven Sisters, located in the constellation Taurus. Visible to the naked eye as a small, shimmering cluster of stars, the Pleiades lies about 440 light-years from Earth and is only around 100 million years old, a cosmic infant by galactic standards. Its stars still glow with youthful blue brilliance, surrounded by faint wisps of reflection nebulae that scatter their light through interstellar dust. The Pleiades have long held a place in human mythology, appearing in the legends of cultures across the world, from the Greeks, who named them after the daughters of Atlas, to the Maori, who called them Matariki and used their rising to mark the new year. Another open cluster, the Hyades, lies nearby in the same constellation and forms the distinctive V-shape of Taurus's head. At about 625 million years old, it is older and more dispersed than the Pleiades, a glimpse of what happens as open clusters age and slowly lose their cohesion. Over time, the gravitational influence of the galaxy pulls these clusters apart, scattering their stars into the Milky Way's disk. Many of the lone stars we see across the night sky, including our Sun, likely began life as part of such a cluster billions of years ago before drifting away to wander on their own. While open clusters represent the Milky Way's youthful, ever-changing population, globular clusters tell the opposite story, a story of ancient endurance. These spherical collections of stars orbit the galaxy far from its luminous disk, residing mostly in the galactic halo. Containing hundreds of thousands to millions of stars, globular clusters are among the oldest known structures in the universe, many dating back more than 12 billion years, almost to the dawn of the Milky Way itself. Their stars are tightly packed, bound by gravity so strongly that they can survive for the entire lifetime of the galaxy. The contrast between these two types of clusters is striking. Open clusters are fragile and fleeting, brilliant but temporary gatherings of newborn stars, while globular clusters are the ancient survivors of a universe that was still finding its form. Open clusters belong to the spiral arms, where gas and dust are abundant and star formation thrives. Globular clusters dwell in the halo, far from the galaxy's active regions, their stars long since aged into cool red giants. Together, they embody the Milky Way's full temporal spectrum, one representing youth and creation, the other, age, and memory. The most famous of all globular clusters is Omega Centauri, an immense, awe-inspiring cluster visible to the naked eye from southern latitudes. Containing roughly 10 million stars and spanning about 150 light-years across, it is so large and massive that some astronomers believe it might not be a true cluster at all, but the remnant core of a small galaxy that the Milky Way devoured long ago. Through a telescope, Omega Centauri appears as a dense, glittering swarm of stars, so tightly packed that near its center they are only a fraction of a light-year apart. Looking at it is like gazing into a stellar metropolis that has endured since the universe's youth. Other notable globular clusters include M13, the Great Hercules Cluster, and 47 Tucanae, both of which contain hundreds of thousands of ancient stars glowing with golden light. Each one acts as a time capsule, preserving the conditions of the early universe. The stars within them have very low metallicities, meaning they lack the heavier elements produced by later generations of stars. This chemical purity tells astronomers that globular clusters formed during the Milky Way's infancy, when the galaxy was assembling itself through mergers and collisions with smaller protogalaxies. The orbits of globular clusters are also key to understanding the Milky Way's history. Many travel in long, elliptical paths that take them far above and below the galactic plane, tracing the shape of the halo and revealing how the galaxy's mass is distributed. Some even appear to have been captured from other galaxies, brought in during ancient mergers. These interlopers serve as fossil evidence of the Milky Way's growth through galactic cannibalism, the process by which larger galaxies absorb smaller ones, incorporating their stars and clusters into their own structure. Both open and globular clusters play essential roles in the Milky Way's ongoing evolution. Open clusters replenish the galaxy with young stars, planets, and the potential for new life. Globular clusters preserve its ancient memory, holding within them the secrets of the early universe. Studying both allows astronomers to piece together a continuous timeline of galactic history, from the earliest epochs after the Big Bang to the present day. And perhaps most beautifully, these clusters remind us that even in the vast emptiness of space, stars are born together, live together, and influence each other's destinies. The Milky Way is not just a collection of isolated points of light. It is a network of communities, each one a chapter in the story of cosmic creation. From the shimmering Pleiades that light our night skies to the ageless grandeur of Omega Centauri, orbiting far beyond the galactic disk, these stellar cities show us that the universe, for all its enormity, is bound together by relationships, history, and shared origins. In every direction we look, some cluster or another shines back at us, bridging the Milky Way's past and present, reminding us that our galaxy is both young and ancient, ever-changing yet timeless. Between the glittering stars, where the night seems to turn pitch black, lies a realm that is far from empty. Though our eyes perceive only darkness, the space between stars, the interstellar medium, is a vast ocean of invisible material that fills every corner of the Milky Way. It's not a true void, but a delicate mixture of gas, dust, and cosmic rays stretching across the galaxy in great clouds, filaments, and diffuse mists. This material is the lifeblood of the Milky Way, the raw substance from which stars are born and to which they ultimately return their remains. In this unseen expanse, the story of stellar creation and destruction is written not in light, but in whispers of hydrogen and dust. The interstellar medium is composed mostly of hydrogen, the simplest and most abundant element in the universe. But this hydrogen exists in various forms depending on temperature and density. In the coldest regions, it collects as neutral hydrogen atoms, Hi, or molecular hydrogen, H2, forming enormous molecular clouds, the dark nurseries where stars are born. These clouds are colossal, spanning tens to hundreds of light years, and can contain enough material to form thousands of suns. To human eyes, they appear as dark patches in the Milky Way, blocking starlight, but in infrared or radio wavelengths, they glow faintly, revealing their intricate internal structure. In the warmer regions between these cold clouds, the gas becomes more diffuse and partially ionized, creating vast interstellar filaments, thread-like structures that stretch for hundreds of light years through space. These filaments weave through the galactic disk like cosmic veins, connecting star-forming regions and distributing material throughout the galaxy. Observations from telescopes like Herschel and Planck have revealed that these filaments are not random. They form an organized network that mirrors the turbulent flow of gas shaped by magnetic fields, supernova explosions, and the galaxy's rotation. It is within these filaments that new stars often begin to form, as gravity slowly pulls the densest knots of material together. But the interstellar medium isn't just made of gas, it's also filled with dust grains and cosmic rays, the high-energy particles that race through space near the speed of light. The dust, made from carbon, silicon, and heavier elements forged in earlier generations of stars, may seem like a hindrance, blocking our view of the galaxy. Yet, it plays a vital role in cooling the gas and allowing molecular clouds to collapse into stars. Cosmic rays, meanwhile, act as a kind of energetic glue, influencing magnetic fields and driving chemical reactions in interstellar space. Even in regions where starlight cannot reach, cosmic rays keep the chemistry of the galaxy alive. Within this invisible environment, the forces of creation and destruction are in constant balance. When massive stars are born, they don't emerge quietly, they come with immense power. Their intense ultraviolet radiation ionizes the surrounding hydrogen, creating glowing regions known as H2 regions. The Orion Nebula, one of the most famous examples, is a perfect showcase of this phenomenon. Here, newborn stars illuminate the gas around them, carving vast cavities in the surrounding molecular cloud and pushing material outward with their stellar winds. These winds, composed of streams of charged particles traveling at thousands of kilometers per second, sweep up the surrounding gas and dust, shaping it into arcs, bubbles, and shells. Over time, this constant interplay of radiation and pressure can blow holes in the interstellar medium, creating enormous voids called superbubbles. Some of these are hundreds of light years wide, formed by multiple generations of massive stars and their explosive deaths. The Milky Way is filled with these cavities, pockets of hot, ionized gas surrounded by denser shells. One such structure, the local bubble, is the very region of space our Sun currently resides in. Stretching roughly 1,000 light-years across, it was likely carved out by ancient supernovae millions of years ago, leaving a low-density cavity that now hosts our solar system and a few nearby stars. The death of massive stars plays an especially dramatic role in shaping the interstellar medium. When a star many times the mass of the Sun reaches the end of its life, it explodes in a supernova, releasing a shockwave that travels outward at incredible speeds. These shockwaves compress and heat the surrounding gas, triggering new waves of star formation while dispersing heavy elements into space. Thus, every supernova is both an ending and a beginning, a violent event that tears apart one star to seed the birth of many others. This cycle of enrichment ensures that with each generation, the galaxy becomes more chemically complex, setting the stage for the formation of planets, moons, and ultimately life. As astronomers map the interstellar medium using radio and X-ray telescopes, they are uncovering the grand architecture of the Milky Way's gaseous skeleton. Vast hydrogen filaments, some stretching for thousands of light years, crisscross the galaxy, forming bridges between its spiral arms. Giant molecular complexes, like the Orion Molecular Cloud and the Carina Nebula, contain regions so dense that gravity will eventually collapse them into entire clusters of stars. Meanwhile, turbulent motions within the gas, driven by stellar winds, rotation, and magnetic fields, continually stir the medium, preventing it from settling into a uniform state. The result is a galaxy that breathes, a living, ever-evolving organism, inhaling and exhaling stars through the rhythm of its own dynamics. It's also through studying the interstellar medium that astronomers have begun to understand galactic ecology, how energy flows through the Milky Way, how material circulates, and how different regions interact over billions of years. The Milky Way's disk is not a static structure, but a complex, self-sustaining system. Stars form, live, and die, releasing gas and dust that enrich the interstellar medium. That material then cools, condenses, and gives rise to new stars. The process repeats endlessly, a cosmic heartbeat pulsing through time. In essence, the space between stars is where the Milky Way's soul resides. It is not empty, but full of potential, a quiet reservoir of creation shaped by gravity, magnetism, and energy. Every glowing star we see in the sky once formed from this invisible matter, and every star will one day give its substance back to it. The interstellar medium is the great recycler of the cosmos, weaving the fabric from which all stellar life emerges. And as we drift through one of its carved-out cavities, surrounded by the remnants of ancient explosions, we are reminded that even in the silence between stars, the galaxy is alive, moving, changing, and endlessly rebirthing itself in the dark. Beyond the luminous spiral arms, far past the glowing disk where most of the Milky Way's stars reside, lies a realm that defies ordinary perception, a vast, nearly invisible sphere known as the galactic halo. This enormous region extends hundreds of thousands of light years in every direction, enveloping the visible galaxy like a ghostly cocoon. Though the halo appears empty and dark, it is, in fact, one of the most mysterious and important components of the Milky Way. It is home not only to ancient stars and globular clusters, the fossils of our galaxy's youth, but also to something far stranger and more elusive: the unseen mass that holds the galaxy together, dark matter. The visible parts of the Milky Way, its stars, nebulae, and glowing spiral arms, make up only a tiny fraction of its total substance. Astronomers long suspected that something hidden was influencing how the galaxy moved. When they studied the orbits of stars and gas clouds, they found something puzzling. The stars in the outer regions of the galaxy were moving far faster than expected. According to the laws of gravity, if the Milky Way's mass came only from the visible stars and gas, those distant stars should have been flung into intergalactic space long ago. Yet they remained bound, orbiting steadily as if held by an invisible hand. This discrepancy could only mean one thing: the galaxy must contain vast amounts of unseen matter, providing the extra gravity needed to keep everything in place. This hidden component, first theorized in the early 20th century and later confirmed through detailed measurements, became known as dark matter. It doesn't emit, absorb, or reflect light, making it invisible to all forms of electromagnetic observation. Telescopes, cameras, and even the most sensitive detectors can't see it directly. Yet its gravitational influence is undeniable. Astronomers estimate that up to 90% of the Milky Way's total mass is made of this mysterious substance. The stars, planets, gas, and dust we can observe, the entire visible galaxy, make up only about 10% of the whole. In other words, the galaxy we see is just the shining tip of an enormous, invisible iceberg. The halo is where most of this dark matter resides. It extends far beyond the Milky Way's visible edge, perhaps out to 300,000 light-years from the galactic center, forming a roughly spherical distribution that surrounds and stabilizes the entire galaxy. It doesn't rotate in the same orderly way as the galactic disk. Instead, it exists as a vast, diffuse cloud of particles that interact through gravity but not through light or electromagnetism. Within this dark halo, small satellite galaxies, like the Magellanic Clouds and dozens of dwarfs, orbit in patterns sculpted by dark matter's gravitational field. Even the paths of distant globular clusters and streams of stars, torn from smaller galaxies, are shaped by its invisible influence. Scientists detect dark matter not by seeing it directly, but by measuring its gravitational effects. When we observe how stars orbit within the Milky Way, or how gas clouds move in the outer regions, we can infer the presence of extra mass that cannot be accounted for by visible matter alone. Similarly, when light from distant galaxies passes near the Milky Way, it bends slightly, a phenomenon known as gravitational lensing. This bending reveals the presence of a hidden gravitational field caused by dark matter. Through these indirect methods, astronomers have been able to map the approximate shape and extent of the Milky Way's dark halo, even though its true nature remains one of science's deepest enigmas. What exactly is dark matter made of? That question continues to baffle researchers. It is not composed of ordinary atoms, since it neither emits nor absorbs light and does not seem to interact with radiation or charged particles. The leading theories suggest it could be made of exotic particles, such as WIMPs, weakly interacting massive particles, or axions, that barely interact with normal matter. Others propose that it might consist of primordial black holes, formed in the earliest moments of the universe. Despite decades of searching, no experiment has yet detected dark matter particles directly, though the evidence for their gravitational presence is overwhelming. The Milky Way, like all galaxies, quite literally floats in a sea of dark matter, an unseen ocean that holds its luminous structure together. In addition to dark matter, the galactic halo also contains ancient remnants of the Milky Way's earliest days, old stars, stellar streams, and globular clusters that orbit the galaxy in vast looping paths. These objects act as test particles, helping astronomers measure the halo's mass and shape. Some of the faintest stars ever discovered belong to this outer halo population, their low metallicity revealing their ancient origins. Many of these stars were likely captured during the Milky Way's long history of galactic mergers, stripped from smaller galaxies that were torn apart by tidal forces. In this way, the halo serves not only as the galaxy's gravitational skeleton, but also as its archive of cosmic archaeology, preserving evidence of its violent and dynamic past. Through computer simulations and cosmic surveys, scientists have come to realize that dark matter halos are fundamental to the very existence of galaxies. Without dark matter, the universe as we know it would never have formed its vast cosmic structures. After the Big Bang, normal matter alone was too sparse and energetic to clump together quickly. It was dark matter, cool, invisible, and massive, that first gathered into large halos under gravity. These halos then acted as gravitational wells, pulling in gas and dust that eventually condensed to form the first galaxies. In this sense, dark matter can be thought of as the cosmic scaffolding upon which the Milky Way and all other galaxies were built. Even today, the Milky Way's dark halo continues to shape its fate. It dictates how fast the galaxy rotates, how it interacts with nearby companions, and even how it will merge with Andromeda billions of years from now. The halo's immense gravity governs the orbital motions of everything within it, from the Sun to the farthest satellite galaxy. We owe our galaxy's stability, and perhaps even the long-term survival of our solar system, to this invisible structure that silently holds the cosmos together. If we could somehow see dark matter, the Milky Way would appear vastly different. Instead of a thin, flat spiral, we would behold a colossal glowing sphere, stretching hundreds of thousands of light years in every direction, faintly shimmering with energy we cannot yet detect. The spiral disk of stars and nebulae would look like a small, luminous whirlpool floating inside a vast, invisible sea. It's a humbling thought that the galaxy we see is only a fraction of what truly exists, and that the forces shaping our universe are largely unseen, unfelt, and unknown. The galactic halo, with its shrouded contents, reminds us that even as we map and measure the cosmos, we still live in a universe of profound mystery. What we call dark matter may simply be a placeholder name for something deeper, something we've yet to comprehend. But its influence is undeniable. It sculpts galaxies, bends light, and anchors the stars themselves. It is the silent framework of existence, the invisible hand that keeps the Milky Way from flying apart, holding together the story of our galaxy in a gravitational embrace that spans eternity. Though we often picture the Milky Way as a serene spiral suspended motionless in space, the truth is far more dynamic. The entire galaxy is in constant motion, a colossal, rotating system of stars, gas, and dark matter swirling through the cosmos with incredible speed and grace. Every part of it, from the dense core near Sagittarius A to the faint outer halo, is moving in a grand gravitational ballet that has been unfolding for billions of years. In this endless dance, no star, no planet, and no atom stands still. Even as we sit here on Earth, the ground beneath our feet, our sun above, and our galaxy itself are all racing through the universe at astonishing velocities. At the heart of it all lies the galactic center, where the supermassive black hole, Sagittarius A, anchors the Milky Way's gravitational structure. Around it, the galaxy's disk spins like a vast cosmic whirlpool, with stars orbiting in concentric paths. The speed at which they travel depends on their distance from the center. Inner stars whip around more quickly, while outer stars move more slowly, though not nearly as slowly as early astronomers expected. The invisible gravity of dark matter keeps them bound in their orbits, maintaining the spiral structure. On average, the stars within the galactic disk move at about 220 kilometers per second around the center. Our Sun, located about 27,000 light-years from the galactic core, is part of this great rotation. It hurtles through space at roughly 828,000 kilometers per hour, about 230 kilometers per second, along its orbit, carrying the entire solar system with it. At that speed, it would take a beam of light only a few minutes to travel the same distance the Sun covers in 1 second. Yet despite this tremendous velocity, the Sun's journey around the galaxy is immense in scale. It takes about 230 million years to complete one full orbit around the Milky Way's center. Astronomers call this period a galactic year. To put that into perspective, the last time our solar system was in this same position in its orbit, the Earth was ruled by dinosaurs. Since its formation 4.6 billion years ago, the Sun has completed roughly 20 orbits around the galaxy. In that time, continents have drifted, species have evolved and gone extinct, and civilizations have risen and fallen, all while our solar system has been quietly gliding through the Milky Way's vast gravitational field. Every revolution is a reminder that even though we think of space as still, our entire existence is carried along on a cosmic journey through the galaxy's swirling expanse. But the motion doesn't stop there. The Milky Way's spiral arms, those majestic curving lanes of stars, dust, and gas, are also in motion, though not in the same way as the stars themselves. The arms are density waves, patterns of higher density that sweep through the galactic disk like ripples on water. Stars and gas clouds move in and out of these arms as they orbit, much like cars passing through a traffic jam. The pattern remains, even though individual objects flow through it. As gas clouds enter these dense regions, gravity compresses them, triggering new waves of star formation. In this way, the spiral arms are not fixed structures, but moving waves of creation, shifting, renewing, and shaping the Milky Way's luminous beauty. And as if the internal motion weren't enough, the entire Milky Way itself is moving through the universe. Relative to the cosmic microwave background, the faint afterglow of the Big Bang, the Milky Way is traveling at an astonishing 600 kilometers per second, about 1.3 million miles per hour. This means that as we spin and orbit within our galaxy, the entire Milky Way is also gliding through space, pulled along by the gravity of nearby galaxy clusters and cosmic structures. We're part of an immense cosmic flow, moving toward a region known as the Great Attractor, a mysterious gravitational anomaly about 150 to 200 million light-years away that is tugging our entire local group of galaxies in its direction. Zooming out even further, the Milky Way is not only rotating and drifting, it's also tilted and warped, slightly bent at its edges, likely due to the gravitational influence of its smaller satellite galaxies and the uneven distribution of dark matter around it. The outer disk undulates gently, giving the galaxy a subtle potato chip shape. As the Milky Way spins, it ripples through space, its stars and gas clouds bobbing up and down through the galactic plane like a vast rotating wave. This motion creates a sense of fluidity across the entire structure, making the galaxy feel alive, ever in motion, ever changing. Within this grand rotation, every object follows its own intricate path. Stars orbit not in perfect circles, but in elongated, tilted trajectories. Clusters and dwarf galaxies weave through the halo, tracing arcs that can take billions of years to complete. Even interstellar gas and dust swirl along complex routes shaped by magnetic fields, stellar winds, and supernova explosions. The Milky Way is like a cosmic clockwork, every component linked by gravity in a harmonious, ever-turning system. For astronomers, mapping these motions provides critical insight into the galaxy's mass and structure. By observing how stars and gas move, scientists can infer the invisible distribution of dark matter in the halo, revealing the unseen architecture of the Milky Way. The precise measurements from missions like Gaia have transformed our understanding of the galaxy's kinematics, showing that its rotation is not perfectly uniform, but subtly influenced by the gravitational tugs of nearby galaxies, like the Large Magellanic Cloud and Sagittarius dwarf galaxy, both of which are slowly merging with it. And just as our galaxy moves, so do its neighbors. The Andromeda galaxy, our nearest large galactic companion, is also in motion, rushing toward the Milky Way at about 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will collide and merge into a new, larger elliptical system astronomers have already nicknamed Milkomeda. Even this monumental event will not stop the cosmic motion. The new galaxy will continue to drift through space, propelled by the same universal forces that have guided its ancestors since time began. So, when you gaze at the Milky Way stretching across a dark sky, know that you are looking at something in motion, something alive. Every twinkling star you see is racing through space, tracing a silent orbit around the galactic core. Every glowing nebula and every faint cloud of dust is caught in the galaxy's eternal rotation. And you, sitting on a small blue planet, orbiting an ordinary star, are also part of this journey, moving at incredible speeds through a universe that never stands still. In the grand symphony of motion that defines the Milky Way, we are all passengers aboard a celestial vessel, spinning and gliding through the dark at breathtaking speed, bound by gravity, and carried forward by forces that reach back to the dawn of creation itself. Though the Milky Way appears serene and stable from our vantage point, its history is anything but peaceful. Beneath its luminous spiral beauty lies a tale of violence, hunger, and transformation, a cosmic predator that has grown and evolved over billions of years by devouring smaller galaxies. The Milky Way is not a static structure that simply formed and remained the same. It is a living, evolving entity, built through countless collisions and mergers that continue even to this day. Every star, every cluster, and even our own sun may be part of the remnants of these ancient cosmic meals that shaped our galactic home. When we look deep into the Milky Way's halo and outskirts, we find the faint traces of its turbulent past. Stellar streams, long, delicate rivers of stars stretching across the sky like cosmic scars. These streams are the remnants of dwarf galaxies and star clusters that the Milky Way once consumed. Over billions of years, as smaller galaxies drifted too close, the Milky Way's immense gravity tore them apart, pulling their stars, gas, and dark matter into its own system. What remains are these ghostly trails, slowly dispersing but still visible to the precise eyes of modern telescopes. One of the most striking examples of this galactic cannibalism is the Sagittarius dwarf galaxy, a small satellite galaxy currently being shredded by the Milky Way's gravity. Located about 70,000 light-years from Earth, this unfortunate neighbor has already been torn apart several times over the past few billion years. Its stars now form looping arcs that wrap around the Milky Way, encircling it in a glowing tidal stream that astronomers have mapped stretching across both hemispheres of the sky. With each orbit, the Sagittarius dwarf loses more of its mass, feeding the Milky Way and enriching its outer regions with new stars and material. Eventually, it will be fully absorbed, its identity erased, its stars assimilated into our galactic family. The Milky Way's appetite, however, is ancient. Astronomers have uncovered evidence of dozens of past mergers that occurred throughout its lifetime. One of the most significant was the merger with the Gaia Enceladus galaxy, a small but massive system that collided with the young Milky Way around 10 billion years ago. This ancient collision dramatically reshaped our galaxy, puffing up its early disk and creating a thick layer of stars now known as the thick disk. The evidence for this event comes from the Gaia Space Observatory, which revealed that many stars in this region have different motions and chemical compositions from the Milky Way's native stars, signatures of their extragalactic origin. Other mergers have left similar imprints. The Helmi stream, discovered in the late 1990s, is another relic of a small galaxy that the Milky Way absorbed roughly 6 to 9 billion years ago. Its stars share unique orbital characteristics and elemental abundances, marking them as the remnants of a once independent system that was gradually torn apart and assimilated. Still more streams, such as the GD1 stream, Orphan stream, and the Anticenter stream, snake across the galactic halo, each one a remnant of an ancient collision, each one a fossil of the Milky Way's relentless hunger. This process of galactic growth is not unique to the Milky Way. It is a fundamental feature of cosmic evolution. In the early universe, galaxies formed in clusters, frequently colliding and merging to form larger, more complex systems. The Milky Way itself likely began as a small proto-galactic cloud about 13.6 billion years ago, slowly accumulating mass by merging with neighboring systems. Each collision added not only stars and gas, but also dark matter, increasing the galaxy's total gravitational pull and helping to stabilize its growing structure. These mergers built up the Milky Way's halo, populated it with globular clusters, and gave it the mass it has today. Even now, this process continues. The Milky Way is surrounded by a swarm of smaller satellite galaxies, including the Large and Small Magellanic Clouds, both of which are currently interacting with our galaxy's outer halo. These two irregular galaxies are slowly being stripped of their gas and stars, forming vast tidal tails such as the Magellanic Stream, which stretches across more than half the night sky. In the distant future, they too will be consumed, their stars incorporated into the Milky Way's outer disk and halo, leaving behind faint stellar rivers that future astronomers may one day trace. It's not only stars that merge. Gas and dust from these collisions also fuel new bursts of star formation. When a smaller galaxy merges with the Milky Way, its gas is compressed and heated as it collides with our own, triggering the birth of new stars in the spiral arms. This is why mergers are both destructive and creative. They tear apart the old while giving rise to the new. Every generation of stars born in the wake of these interactions carries with it the chemical memory of past galaxies, enriched by their unique elemental signatures. In this way, the Milky Way is not a singular entity, but a mosaic of many galaxies, each contributing to the composition and beauty of the one we now call home. The process of galactic cannibalism is slow, unfolding over billions of years, too gradual for us to witness directly. Yet, through careful mapping and simulation, astronomers can rewind the Milky Way's history, watching in virtual form as it consumes its neighbors, grows in size, and evolves into the majestic spiral we see today. These simulations suggest that in its lifetime, the Milky Way has devoured at least a dozen major galaxies and hundreds of smaller ones. Each of these mergers has left behind faint traces, streams, clusters, and unusual star motions that together form a record of our galaxy's violent evolution. Even as we speak, this process hasn't stopped. The Sagittarius dwarf continues its slow demise, the Magellanic Clouds inch closer, and faint, newly discovered dwarf galaxies like Tucana 3 and Antlia 2 are already showing signs of being distorted by the Milky Way's tidal forces. Our galaxy, though seemingly tranquil in the night sky, is a cosmic predator, consuming its companions piece by piece, growing ever more massive and complex with each passing epoch. And yet, there's a poetic symmetry to it all. The same gravitational forces that destroy galaxies also weave them together. Every collision, every merger, is an act of transformation. One galaxy giving its stars to another, creating something greater than either could have been alone. The Milky Way itself is a product of this eternal cycle, born from the remnants of ancient systems and destined, in turn, to merge once more. Because even as it feeds on smaller galaxies, a far grander encounter looms on the horizon, an event that will redefine our place in the cosmos, the inevitable collision with Andromeda. The Milky Way, for all its grandeur and motion, is not eternal in its current form. As it glides through the cosmos, bound by the unseen web of gravity, it is on a slow but inevitable collision course with its closest galactic neighbor, the Andromeda Galaxy. This colossal event, predicted to occur in about 4.5 billion years, will forever change the face of our galaxy and the night sky. Andromeda, known to astronomers as Messier 31, M31, is currently about 2.5 million light-years away, visible to the naked eye as a faint smudge of light in the constellation of Andromeda. But that smudge is not static. It's moving toward us at roughly 110 kilometers per second, and its trajectory ensures that one day, the two largest galaxies in the local group will collide in a breathtaking cosmic merger. At first glance, the idea of two galaxies colliding sounds catastrophic. Billions of stars crashing into one another, planetary systems torn apart, and unimaginable chaos. Yet the truth is both more astonishing and far more serene. Despite their immense sizes, galaxies are made mostly of empty space. The distances between stars are so vast that when the Milky Way and Andromeda finally meet, very few, if any, stars will actually collide. Instead, the galaxies will pass through each other like ghosts, their stars sailing silently by as gravitational tides twist and reshape their structures. It will be a dance of giants, a slow spiraling embrace that unfolds over billions of years, transforming two magnificent spirals into one enormous new creation. As Andromeda approaches, its size in our night sky will gradually increase. Millions of years from now, our descendants, or whatever forms of life exist on Earth then, will see it growing brighter, turning from a faint blur into a spectacular glowing disk that dominates the heavens. Eventually, as the two galaxies draw near, their shapes will begin to distort under each other's gravitational pull. Spiral arms will stretch and warp, flinging streams of stars into long tidal tails that arc across space like luminous ribbons. The orderly disks of both galaxies will unravel, and their gas clouds will collide and compress, igniting waves of intense star formation. The night sky will be ablaze with new light, as countless stars are born in the aftermath of cosmic chaos. Over time, the Milky Way and Andromeda will merge into a single, massive galaxy. Astronomers have already given this future structure a name, Milkomeda, or sometimes Milkdromeda, a vast elliptical or lenticular galaxy that will shine even brighter than either of its predecessors. The merger will take place over the course of roughly 2 billion years, as the two galaxies pass through each other multiple times before finally coalescing into one. The black holes at their centers, our own Sagittarius A and Andromeda's much larger central black hole, which is about 100 million solar masses, will spiral toward each other as well. In the final stages of the merger, they will collide and merge into an even more massive, supermassive black hole, unleashing powerful gravitational waves that ripple through space-time. Though this sounds apocalyptic, from our solar system's perspective, the event may be surprisingly calm. The odds of the Sun directly colliding with another star are extraordinarily low, thanks to the immense distances between stars, comparable to 2 grains of sand in an entire football field missing each other even when flung at high speed. However, the gravitational interactions from passing stars could subtly alter the orbits of planets, potentially changing the layout of our solar system over long timescales. Some simulations suggest the Sun might even be flung into a new orbit, far from the galactic center, becoming part of a tidal stream in the merged galaxy. Yet, Earth itself may not even be around by then. The Sun, nearing the end of its 10 billion year life, will have already expanded into a red giant, possibly engulfing our planet. For a time, the merging galaxies will create a sky of unparalleled beauty. Imagine looking up and seeing a vast, glowing swirl of stars filling the heavens, with streams of light stretching from horizon to horizon. The dark lanes of the Milky Way will be replaced by a brilliant, chaotic panorama of merging galactic cores, nebulae, and star clusters, a view unlike anything our species has ever known. The merger will be slow, majestic, and awe-inspiring, a display of cosmic evolution on the grandest scale. When the dust settles and the two galaxies finally stabilize, Milkomeda will emerge as a colossal elliptical galaxy, a smooth, rounded system of stars, stripped of the spiral arms that define the Milky Way today. Much of the interstellar gas and dust will have been consumed in the starburst phase, leaving behind an older, redder population of stars. This new galaxy will likely be about twice the size of the Milky Way, containing over 1 trillion stars and spanning nearly 200,000 light-years across. Its central black hole will be one of the most massive in the local universe, and its gravitational field will extend farther than ever before, pulling in the remaining dwarf galaxies of the local group to form one grand, unified structure. In the far future, as the universe continues to expand, this merged galaxy will stand largely alone in an ever-growing cosmic void. The light from other galaxies will fade away as the space between them stretches faster than light can travel. To any intelligent beings living in Milky billions of years from now, the universe may appear far emptier than it does to us. A lonely, self-contained island of stars surrounded by darkness. They might look to the sky and see no evidence of other galaxies at all, unaware that their home was once the result of countless mergers in a once crowded cosmos. The collision with Andromeda reminds us that galaxies are not eternal monuments but evolving systems, constantly changing, consuming, and creating. What we call the Milky Way is only one chapter in a much larger story, one that will continue long after our time. When the two galaxies finally merge, they will carry with them the histories of trillions of stars, billions of worlds, and perhaps countless civilizations, woven together into a new cosmic tapestry. And even though our galaxy will lose its spiral arms and familiar shape, it will gain something far greater: permanence. For Milky will endure for trillions of years, slowly dimming as its last stars burn out, yet remaining as a silent monument to everything that ever existed within its stars. It will be the final, eternal form of the Milky Way's legacy, a galaxy born of collision, but destined for quiet majesty in the deep time of the universe. At the very heart of the Milky Way lies a region of breathtaking complexity and mystery, a place so extreme that the laws of physics seem to teeter on the edge of comprehension. This is the galactic center, the beating core of our galaxy, a turbulent, radiant realm where gravity, light, and matter collide in one of the most intense environments known to science. If the Milky Way were a city, this would be its downtown, densely packed, chaotic, and full of energy. Home to millions of stars, crammed into a volume only a few dozen light years across, all revolving around a single, invisible powerhouse, Sagittarius A, the supermassive black hole at the galaxy's core. From Earth, we can't see the galactic center in visible light. It's completely obscured by massive dust clouds that blanket the inner regions of the Milky Way. For centuries, astronomers saw only an opaque band of darkness when they looked toward the constellation Sagittarius, unaware that behind those dark veils lay the gravitational heart of our galaxy. It wasn't until the invention of infrared, radio, and X-ray telescopes that we finally pierced the dust, revealing a hidden world of intense energy and furious motion. What we found there changed our understanding of the galaxy forever. The central bulge of the Milky Way, the dense, roughly spherical region surrounding Sagittarius A, is unlike any other part of the galaxy. It's a crowded metropolis of stars, star clusters, and interstellar gas, with stellar densities 1,000,000 times higher than those near our Sun. In some areas, stars are packed so closely together that if you were somehow standing on a planet there, the night sky would blaze with hundreds of suns, casting enough light to banish darkness entirely. These stars are ancient, many of them over 10 billion years old, but intermingled with them are much younger, hotter, and more massive stars, formed from gas clouds compressed by the fierce gravity and energy of the galactic core. Orbiting at the very center of this chaos are thousands of stars whipping around the black hole at incredible speeds. Some travel so fast that they complete an entire orbit in just a few years. The star S2, one of the most famous of these cosmic daredevils, takes only 16 years to circle Sagittarius A, a journey that would take the Sun 230 million years if it were somehow that close. At its nearest point, S2 races past the black hole at over 7,600 kilometers per second, fast enough to travel from Earth to the Moon in under a minute. Watching stars like S2 move around an invisible point was one of the key discoveries that confirmed the existence of a supermassive black hole at the Milky Way's core. But this central region isn't just remarkable for its stars. It's also a cauldron of intense radiation, magnetic fields, and cosmic violence. The area around Sagittarius A emits powerful radio waves, X-rays, and gamma rays, generated by gas and dust spiraling inward at near light speed before being swallowed by the black hole. These emissions fluctuate unpredictably, sometimes brightening or fading within hours, suggesting complex and dynamic processes near the event horizon, where gravity is so strong that not even light can escape. In 2022, the Event Horizon Telescope collaboration gave us our first glimpse of this hidden heart, an image of the glowing ring of superheated plasma surrounding the black hole's shadow, a direct view into the Milky Way's gravitational engine. Surrounding the black hole is a maelstrom of energy. Accretion disks, relativistic jets, and radio bursts that defy easy explanation. Astronomers have observed mysterious flashes and bursts of radio waves coming from the galactic center, some lasting only milliseconds, others repeating irregularly. These signals may be produced by magnetars, highly magnetized neutron stars, or by interactions within the turbulent gas clouds orbiting near the black hole. Yet many of these bursts remain unexplained, hinting at phenomena we have yet to fully understand. Occasionally, X-ray flares erupt from Sagittarius A with no clear trigger, suggesting that even now, the Milky Way's heart hides secrets beyond our current physics. The galactic center is also home to some of the most massive and compact star clusters known in our galaxy. Among them are the Arches cluster and the Quintuplet cluster, each containing thousands of massive young stars formed in the last few million years, incredibly young by galactic standards. These clusters are so dense and luminous that they shape their surroundings, driving powerful stellar winds that carve cavities in the gas and dust around them. In the same region lies the central molecular zone, a massive ring of dense molecular gas encircling the inner galaxy. This zone is a cosmic factory of star formation, constantly giving birth to new stars, even as others die in spectacular supernova explosions. Despite its brilliance and violence, the galactic center operates in a delicate balance. Gravity pulls matter inward, while radiation pressure, magnetic fields, and stellar winds push outward, creating a dynamic equilibrium that has lasted for billions of years. It is a place of constant creation and destruction, where stars live fast and die young, their deaths feeding the next generation of celestial life. What makes the center even more intriguing is how much remains unknown. The supermassive black hole's feeding habits, for instance, are erratic. At times, it appears relatively quiet, absorbing little material, while at other times, it flares up dramatically. Evidence suggests that in the distant past, Sagittarius A may have been far more active, perhaps even a quasar, a blazing beacon visible across the universe. X-ray echoes in nearby molecular clouds indicate that powerful outbursts from the black hole occurred thousands of years ago, lighting up the inner galaxy like a cosmic lighthouse. What caused these events, and whether they will happen again, remains a mystery. The galactic center's influence extends far beyond its immediate surroundings. The gravitational pull of the central bulge and black hole helps to anchor the galaxy's overall structure, keeping the spiral arms stable and shaping the motions of stars across the Milky Way. It is the Milky Way's gravitational heart, a dense, turbulent, radiant hub that orchestrates the motions of hundreds of billions of stars. To peer into this hidden region is to glimpse the engine of the galaxy, the place where gravity reigns supreme, where stars are born and die in rapid succession, and where the mysteries of physics stretch toward their limits. For all our technological progress, the galactic center still defies full understanding. It is both the Milky Way's most dangerous and most beautiful place, a region of extremes that reminds us how small and fragile we are amid the forces that govern the cosmos. And as we continue our journey outward from this brilliant, chaotic heart, we find calmer realms, glowing clouds of gas and dust where stars are born under gentler conditions. These are the nebulae, the cradles of creation scattered throughout the Milky Way, where the next generation of suns begins to shine. Beyond the blinding brilliance of the galactic center, the Milky Way stretches outward into regions of breathtaking beauty and calm, vast cosmic nurseries where stars are born from clouds of gas and dust. These regions, known as nebulae, are the cradles of creation, immense interstellar clouds where gravity, chemistry, and radiation come together to ignite the birth of new suns. Each nebula tells a different story, a chapter in the ongoing saga of stellar evolution that has shaped our galaxy for billions of years. They are both the beginning and the continuation of the Milky Way's life cycle, glowing, turbulent arenas where the galaxy breathes new light into the universe. Nebulae come in many forms, each reflecting a different stage of this process. Some, like the Orion Nebula, are emission nebulae, glowing with vivid colors as ultraviolet light from nearby young stars energizes the surrounding hydrogen gas. Others are reflection nebulae, where starlight bounces off fine dust grains, scattering blue hues across the darkness. There are also dark nebulae, cold, dense clouds that block light entirely, their forms silhouetted against brighter backgrounds. Together, these nebulae form the scaffolding of creation, shaping the spiral arms of the Milky Way and continually renewing its stellar population. Among the most famous of these is the Orion Nebula, perhaps the most well-studied and easily visible star-forming region in our galaxy. Located about 1,344 light-years away in the sword of the Orion constellation, it appears as a faint, glowing patch to the naked eye, but reveals astonishing complexity through a telescope. Spanning 24 light-years across, the Orion Nebula is home to the Trapezium Cluster, a tight group of massive young stars whose fierce radiation illuminates and sculpts the surrounding gas. Within its depths, astronomers have observed hundreds of protoplanetary disks, swirling clouds of dust and gas surrounding infant stars, offering a direct glimpse into the birth of solar systems. In a sense, the Orion Nebula is a mirror of our own beginnings. Around 4.6 billion years ago, our Sun likely formed in a similar nebula, coalescing from the collapse of a dense gas cloud triggered by the shockwave of a nearby supernova. Long after dispersing, that ancestral nebula left behind the raw material that built our planets, oceans, and, ultimately, life itself. Further out in the Milky Way lies one of the most iconic and awe-inspiring star-forming regions ever observed, the Eagle Nebula, home to the legendary Pillars of Creation. Located about 7,000 light-years away in the constellation Serpens, the Eagle Nebula is a vast cluster of gas, dust, and newborn stars. The pillars themselves, made famous by the Hubble Space Telescope's 1995 image and later revisited in stunning detail by the James Webb Space Telescope, are towering columns of interstellar gas stretching 5 light-years tall. Within these colossal structures, stars are being born right now, as gravity pulls material together inside dense knots known as Bok globules. Radiation from nearby young, massive stars erodes and sculpts the pillars, slowly consuming them, even as new stars emerge within. The pillars of creation are both a birth and a death scene, the raw forces of creation and destruction entwined in a single cosmic sculpture. Even more colossal and chaotic is the Carina Nebula, one of the largest and most active stellar nurseries in the Milky Way. Located about 7,500 light-years away in the constellation Carina, this nebula spans more than 300 light-years and is home to some of the most massive and luminous stars known, including the volatile giant Eta Carinae. Eta Carinae is a star more than 100 times the mass of the Sun, currently in a state of unstable fury, shedding enormous amounts of material as it nears the end of its life. The nebula surrounding it glows in vibrant hues of pink, blue, and gold, illuminated by the ultraviolet light of thousands of newborn stars. The Carina Nebula is a stellar nursery on a colossal scale, a churning, radiant womb where stars of every size are born in clusters, each generation giving rise to the next. These nebulae, Orion, Eagle, and Carina, are among the Milky Way's most magnificent laboratories for understanding how stars and planets form. Within them, the delicate interplay of gravity, radiation, and turbulence determines which parts of the cloud collapse into stars and which are dispersed into space. As gas contracts under gravity, its temperature rises until nuclear fusion ignites in the core, marking the birth of a new star. Surrounding material flattens into a rotating disk from which planets, moons, and asteroids eventually form. Over millions of years, radiation and stellar winds from young, hot stars blow away the remaining gas, revealing the newborn cluster and dispersing the nebula, leaving behind only stars and planetary systems. This cycle of birth and dispersal ensures the Milky Way remains a living, evolving system. When massive stars eventually die in supernova explosions, they return their enriched material, carbon, oxygen, iron, and other heavy elements, to the interstellar medium. These elements then mix with hydrogen and helium in new clouds, ready to give rise to the next generation of stars. Every nebula, therefore, is both an ending and a beginning, a cosmic recycling plant where the ashes of old stars become the seeds of new ones. In the infrared and radio wavelengths, astronomers have discovered that the Milky Way is filled with such star-forming regions. From the Rosette Nebula in Monoceros to the Lagoon Nebula in Sagittarius, each glows with the heat of newborn stars hidden within their dusty cocoons. These regions trace the spiral arms like jewels, marking the places where the galaxy's gas is most active and alive. Without them, the Milky Way would be a dead, static system, a collection of old stars slowly fading into the darkness. Instead, it pulses with renewal, its nebulae ensuring that light continues to fill the cosmos. And somewhere in the distant past, deep in a nebula not unlike Orion or Carina, our Sun was born. It emerged from a collapsing cloud of gas, surrounded by a swirling disk that would eventually form the planets: Mercury, Venus, Earth, Mars, and the rest. Long after the nebula that birthed us dispersed into space, the memory of that origin lives on in the atoms that make up our world. Every tree, every mountain, every heartbeat carries within it the story of a nebula, the echo of the stars that came before us. When we gaze upon these luminous clouds through our telescopes or see their images from space observatories, we're not just looking at distant celestial objects, we're witnessing the process that made us possible. Nebulae are the wombs of creation, the engines of renewal, and the enduring promise that even in the cold vastness of the galaxy, there is always new light waiting to be born. And as stars continue to emerge from these nebulae, many will host planets of their own, worlds perhaps like ours, orbiting distant suns within the Milky Way's spiral arms. These exoplanets are the next frontier of discovery, where science and imagination meet in the search for other homes among the stars. Over the past few decades, one of humanity's most profound realizations has transformed our view of the Milky Way. Planets are everywhere, What once seemed like an extraordinary rarity, a star with orbiting worlds like our Sun and its planets, is now understood to be the norm. Thanks to advances in telescope technology and the success of missions like Kepler and TESS, astronomers have discovered thousands of exoplanets, planets orbiting stars beyond our solar system, and the evidence suggests that nearly every star in the Milky Way has at least one planet. If our galaxy contains more than 200 billion stars, that means it could easily host over 100 billion planets, and perhaps even more. These worlds come in an astonishing variety. Some are gas giants like Jupiter, bloated and stormy with thick atmospheres of hydrogen and helium. Others are super-Earths, rocky planets larger than our own, with strong gravity and potentially vast oceans. There are lava worlds orbiting perilously close to their stars, ice giants drifting in the cold outer regions of their systems, and even rogue planets, lonely wanderers that drift through space after being ejected from their home orbits. The Milky Way, it seems, is teeming with worlds, each shaped by the same cosmic processes that once formed our own. Perhaps the most exciting discovery is the realization that there may be billions of Earth-like planets, small, rocky worlds orbiting within the habitable zones of their stars, where temperatures could allow liquid water to exist. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of these worlds. By observing tiny dips in starlight as planets passed in front of their stars, Kepler identified more than 2,600 confirmed exoplanets, with thousands more candidates still under review. From this data, astronomers estimate that as many as 1 in every 5 Sun-like stars could have an Earth-sized planet in its habitable zone. Among the most intriguing of Kepler's discoveries is Kepler 452b, often called Earth's cousin. Located about 1,400 light-years away in the constellation Cygnus, this planet orbits a star very similar to our Sun, though slightly older and brighter. Kepler 452b is about 60% larger than Earth, placing it in the category of a super-Earth. It lies within its star's habitable zone, meaning that, theoretically, it could have liquid water on its surface. While we don't yet know if it has an atmosphere or oceans, its discovery was a profound reminder that Earth may not be unique, that other temperate worlds, potentially capable of supporting life, exist scattered across the galaxy. Another fascinating system is TRAPPIST-1, a dim, cool red dwarf star about 40 light-years away. Around it orbit 7 Earth-sized planets, 3 of which are firmly within the star's habitable zone. The TRAPPIST-1 system has captured scientists' imaginations because it's both nearby and remarkably compact. All 7 planets orbit closer to their star than Mercury does to the Sun, yet their cooler host allows some of them to maintain moderate temperatures. Observations from the James Webb Space Telescope are now analyzing their atmospheres, searching for hints of water vapor, carbon dioxide, or other chemical fingerprints of life. It's one of the most promising targets in the ongoing search for habitability beyond Earth. The potential for life in the Milky Way doesn't depend only on whether a planet lies in the right zone around its star, but also on where its star lies within the galaxy. Astronomers refer to this as the Galactic Habitable Zone, a broad region between the dangerous, radiation-rich inner galaxy and the barren, low metallicity outer edges. Too close to the galactic center, and stars are bombarded by supernovae, gamma-ray bursts, and gravitational instability. Too far out, and there aren't enough heavy elements to form rocky planets. Our Sun's location, about 27,000 light-years from the center, appears to be just right, far enough from destructive forces, yet rich enough in the materials that make life possible. If intelligent life exists elsewhere in the Milky Way, it may well be concentrated within this same Goldilocks zone of the galaxy. And while our search is still in its infancy, every year brings new discoveries that challenge our assumptions. Astronomers have found planets orbiting binary star systems, proving that worlds can exist even in complex gravitational environments. Others have discovered planets around dead stars like white dwarfs, suggesting that planetary systems can survive or reform even after their stars die. Some planets orbit so close to their stars that their atmospheres are being stripped away, while others are so distant that they exist in perpetual twilight. The diversity of these worlds reminds us that nature's creativity knows no bounds. The implications of all this are staggering. If just 1% of the Milky Way's Earth-like planets harbor life, that would mean 1 billion living worlds in our galaxy alone. Even if intelligent civilizations are exceedingly rare, the numbers are still enormous. Somewhere among the spiral arms, perhaps in the Perseus or Scutum Centaurus arm, there may be worlds with oceans, forests, clouds, and skies not unlike our own. Some may be just beginning their evolutionary journey, while others could be ancient and advanced beyond our imagination. The search for these worlds is not only a scientific pursuit, it is also deeply philosophical. Every exoplanet we discover expands our sense of possibility, reminding us that Earth is not the center of the universe, but one thread in a vast cosmic tapestry. The Milky Way is not merely a collection of stars, it is a garden of worlds, a place where the conditions for life may have arisen countless times across billions of years. And as we continue to map these distant planets, we move closer to answering one of humanity's oldest and most profound questions. Are we alone? The answer, written across the galaxy's spiral arms, may already be waiting, shimmering in the light of a distant star, orbiting quietly in a system much like our own. While stars and nebulae paint the Milky Way with visible beauty, much of the galaxy's true energy exists in invisible form, in streams of high-energy particles and vast, unseen magnetic fields that permeate every corner of space. These are the cosmic rays and magnetic fields of the Milky Way, powerful, silent forces that shape its structure, influence its evolution, and even touch the fragile atmosphere of our own planet. Though we can't see or feel them directly, they form the galaxy's invisible skeleton and bloodstream, connecting every star, cloud, and planet in a web of charged energy. Cosmic rays are among the most energetic and mysterious travelers in the universe. They are primarily composed of protons and atomic nuclei, the building blocks of matter, accelerated to nearly the speed of light by powerful cosmic events. Many originate from supernova explosions, when massive stars end their lives in violent bursts that send shockwaves rippling through interstellar space. Others are born near neutron stars, pulsars, or even black holes, where intense magnetic fields fling particles outward with unimaginable force. Once launched, these high-energy particles streak across the galaxy, bouncing off magnetic fields and colliding with atoms in interstellar gas, creating a diffuse, invisible glow of radiation that fills all of space. Despite their name, cosmic rays are not rays at all. They're particles, tiny but potent, capable of carrying energies millions of times greater than those produced in human-made accelerators. Some travel from nearby supernova remnants like the Vela pulsar or the Cygnus loop, while others have journeyed from beyond the Milky Way itself, crossing intergalactic space for millions of years before reaching us. When they finally strike Earth's atmosphere, they create showers of secondary particles that cascade down to the surface, a constant, gentle rain of cosmic energy. At any given moment, cosmic rays are striking our planet from all directions. Most are deflected by Earth's magnetic field, which acts as a shield, funneling charged particles toward the poles, where they sometimes produce dazzling auroras, the northern and southern lights. But not all are stopped. Some penetrate the atmosphere, creating new particles such as muons and neutrinos that pass harmlessly through our bodies every second. For spacecraft and astronauts, however, these energetic particles pose a real danger. Prolonged exposure can damage electronics, disrupt instruments, and increase radiation risk. Yet cosmic rays are more than a threat. They're a vital part of the Milky Way's ecosystem. They play an essential role in heating interstellar gas, driving chemical reactions in space, and even influencing star formation. As they move through molecular clouds, cosmic rays ionize atoms and molecules, helping to trigger the collapse of gas that leads to the birth of new stars. In a sense, they act as both the destroyers and creators of cosmic life, contributing to the balance of energy that sustains the galaxy. The paths these particles follow are not straight lines, but twisting, tangled trajectories, shaped by the Milky Way's immense magnetic field. This magnetic field is a vast, unseen structure extending thousands of light years above and below the galactic plane. Though incredibly weak, only about 1/1000th the strength of a refrigerator magnet, it's enough to steer charged particles across cosmic distances. It's generated by the movement of ionized gas within the galaxy. In much the same way, Earth's magnetic field is produced by the motion of molten metal in its core. The Milky Way's magnetic field is both ordered and chaotic. Large-scale field lines spiral around the galaxy, following its rotation and forming a pattern that mirrors the spiral arms. On smaller scales, turbulence from supernova explosions and stellar winds twists and distorts the field, creating knots and filaments of magnetized plasma. These magnetic structures shape how gas flows through the interstellar medium, influencing where stars can form and how cosmic rays move. Without them, the galaxy's delicate balance of matter and energy would collapse into chaos. Scientists have learned to map this invisible structure using radio telescopes, which can detect the faint polarized light emitted by electrons spiraling along magnetic field lines. Observations from missions like Planck and LOFAR have revealed intricate patterns of magnetism woven throughout the Milky Way's disk and halo. Even the enormous Fermi bubbles, gigantic lobes of high-energy plasma extending 50,000 light-years above and below the galactic center, are thought to be shaped and confined by the galaxy's magnetic field, remnants of ancient outbursts from Sagittarius A. On Earth, the influence of cosmic rays and magnetic fields extends beyond astronomy. Changes in cosmic ray intensity, for instance, may subtly affect our planet's climate and atmosphere. When cosmic rays strike air molecules, they create charged particles that can influence cloud formation, a process scientists are still studying. Over long timescales, fluctuations in the Sun's magnetic activity can modulate the amount of cosmic radiation reaching Earth, linking solar cycles to patterns in weather and radiation exposure. The cosmic and the terrestrial are, in this way, intimately connected. Spacecraft exploring the outer solar system, like Voyager 1 and Voyager 2, have even measured the point where the Sun's magnetic influence gives way to that of the galaxy, the heliopause. Beyond this boundary, cosmic rays from interstellar space flow freely, unshielded by the solar wind. When Voyager 1 crossed into this region in 2012, it entered the domain of the Milky Way's true magnetic field, the invisible ocean that surrounds and sustains our galaxy. Cosmic rays and magnetic fields remind us that the Milky Way is not a quiet or passive place. It is an electromagnetic symphony, full of motion, radiation, and invisible power. Every beam of light, every particle of matter, and every magnetic line of force is part of a dynamic system that connects the smallest atoms to the grandest galactic structures. These unseen forces ripple across space, linking stars and planets in ways we are only beginning to understand. They are, in essence, the heartbeat of the galaxy, pulsing, guiding, shaping. a constant reminder that even in the void between stars, the Milky Way is alive with invisible energy. When we step outside on a dark, moonless night, far from the cities, far from the glow of human lights, and look up, we can see one of the most breathtaking sights in all of nature, a glowing river of light stretching across the sky. This soft, milky band, sprinkled with countless stars and threaded with dark lanes of dust, is our home galaxy seen from within, the Milky Way itself. What appears to the naked eye as a faint, hazy cloud is, in truth, the combined glow of billions of distant stars, woven together into the great spiral disk that we call home. From Earth, we view the Milky Way edge on, peering through the thickness of its disk. When we gaze toward the constellations Sagittarius and Scorpius, we're looking inward, toward the galactic center, where the stars are densest and the light brightest. Turn the other way, toward Orion or Perseus, and we're looking outward, toward the galaxy's quieter outskirts. The bright band we see is not uniform. It ripples with brighter regions and dark patches, the result of interstellar dust clouds blocking starlight and shaping the galaxy's luminous texture. In these dark rifts, hidden star nurseries are quietly forming the next generation of suns. Unfortunately, this magnificent sight, once familiar to all humanity, has become a rarity. Today, over 80% of the world's population lives under light-polluted skies, where city lights drown out all but the brightest stars. In most urban areas, the Milky Way is completely invisible, erased by the artificial glow of modern civilization. What was once a nightly reminder of our place in the cosmos has faded from view for billions of people, lost behind a veil of human brightness. Yet, in places where the night remains dark, the Milky Way still reveals itself in all its splendor. Some of the best locations on Earth to see it are the Atacama Desert in Chile, where the air is dry and clear, Mauna Kea in Hawaii, high above the clouds, and remote regions like Namibia's Namib Desert, New Zealand's South Island, and the Australian outback. From these vantage points, the galaxy arches across the entire sky, its light so rich and detailed that it seems to have depth, a three-dimensional glow stretching into infinity. You can trace its bulging core, see faint colors within its haze, and even detect the subtle glow of star clusters and nebula nestled within its arms. For ancient peoples, this luminous band inspired countless myths: a celestial river, a bridge to the afterlife, or the trail of a great cosmic fire. Long before telescopes, humans understood intuitively that the Milky Way connected them to something vast and eternal. And in truth, it does. Every atom in our bodies, every grain of dust on Earth, was once part of the same galactic cycle that fuels those distant stars. To stand beneath the Milky Way is to see our home from the inside, not just as inhabitants of Earth, but as citizens of a galaxy. Its light is ancient, its story immense, and its beauty a reminder of how small yet extraordinary our place in the cosmos truly is. And as we look upon it, we also look back through time, just as those who came before us did, to wonder how it came to be, how we discovered it, and how we continue to unravel its mysteries through the power of observation. Long before science gave the Milky Way its name or explained its nature, ancient peoples across the world looked up at that hazy ribbon of light and wove stories to explain it. To them, it wasn't a galaxy of stars. It was a pathway of spirits, a celestial river, or a scar across the heavens left by divine hands. The Greeks called it Galaxias Kyklos, meaning milky circle, from which the word galaxy itself was born. In China, it was known as the Silver River, where lovers separated by the gods, represented by the stars Vega and Altair, could meet once a year. The Mayans saw it as the World Tree, connecting the heavens and the underworld. And among the Aboriginal peoples of Australia, The Milky Way was a cosmic emu, its dark dust lanes forming the bird's body across the sky. For thousands of years, humanity revered this glowing band without truly understanding it. It was only in the 17th century, with the invention of the telescope, that its true nature began to emerge. In 1610, the great Italian astronomer Galileo Galilei turned his small refracting telescope toward the Milky Way, and what he saw forever changed our perception of the universe. What had appeared as a cloudy mist to the naked eye resolved into countless individual stars, too faint and distant to be seen otherwise. Galileo wrote with astonishment that the Milky Way was a congeries of innumerable stars, realizing for the first time that the night sky's diffuse glow was not a cloud, but an ocean of suns. Over the next few centuries, as telescopes grew more powerful, astronomers mapped the stars and began to understand the Milky Way's shape and scale. In the late 18th century, William and Caroline Herschel used star counts to suggest that we live within a flattened, disk-like system of stars, an early sketch of the Milky Way's structure. Later, in the 20th century, astronomers like Harlow Shapley measured the distribution of globular clusters and discovered that the Sun was not at the center of the galaxy, but instead orbiting tens of thousands of light-years away. A humbling revelation that repositioned humanity from the center of creation to the outskirts of a cosmic spiral. The arrival of modern telescopes revolutionized our understanding even further. The Hubble Space Telescope, launched in 1990, gave us our first clear view of the Milky Way's stars and nebulae from above Earth's blurring atmosphere. Hubble's deep-field observations also revealed that our galaxy is just one among trillions in the observable universe. A staggering realization that expanded our cosmic perspective yet again. In more recent years, missions like the Gaia Space Observatory have transformed our understanding of the Milky Way's structure and motion. Launched by the European Space Agency in 2013, Gaia is creating a three-dimensional map of over 1 billion stars, measuring their positions, distances, and velocities with unprecedented precision. Through Gaia's data, astronomers have traced the spiral arms, discovered ripples in the galactic disk caused by past collisions, and identified stellar streams, the lingering remnants of smaller galaxies the Milky Way once devoured. It's as though we've gone from a rough sketch of our home to a dynamic, living map that captures its movement through time. And now, with the James Webb Space Telescope, JWST, humanity has opened an entirely new window onto the Milky Way. Operating in infrared light, Webb can see through the dense dust clouds that hide the galaxy's core, revealing regions where stars are being born and the intricate structures of nebulae. It has peered into the galactic center itself, capturing the chaotic dance of stars and gas around Sagittarius A, and is now studying the chemical fingerprints of exoplanet atmospheres, searching for signs of habitability and perhaps even life. Each generation of instruments brings us closer to understanding not just what the Milky Way looks like, but how it evolves and breathes. From radio telescopes that trace invisible hydrogen gas to X-ray observatories that detect high-energy events near black holes, our view of the galaxy is now multi-dimensional, spanning the entire electromagnetic spectrum. What once appeared as a simple band of light has become a detailed, dynamic masterpiece, a galaxy with structure, history, and purpose. And yet, for all our progress, the Milky Way continues to surprise us. Gaia's precise measurements have revealed waves in the galactic disk, echoes of ancient collisions. Hubble has uncovered vast stellar halos extending far beyond what we once imagined. JWST continues to show us that even the darkest clouds are alive with activity. Every new image and data release reminds us that discovery is not finished, that the Milky Way, like the universe itself, is far from static. Our journey of understanding began when our ancestors simply looked up in wonder. It continues now with instruments orbiting above our planet, mapping the galaxy in exquisite detail. And as we learn more about the Milky Way, its origins, its structure, its destiny, we are, in a way, learning about ourselves. For we are not separate from the galaxy, we are part of it. Every human, every atom, every spark of consciousness is bound to this great spiral of stars, orbiting quietly in an endless cosmic dance. And as our tools grow sharper and our curiosity deeper, we move toward one final realization: that the Milky Way, vast as it is only one among 2 trillion galaxies in the universe. Which leads us to the greatest reflection of all: our place in the infinite. As we come to the end of this journey through the Milky Way, it's humbling to realize just how vast, and yet how intimately connected, our place in the universe truly is. We began this story in our local neighborhood of stars, tracing the galaxy's swirling arms, its hidden structures, and its luminous heart. We've explored black holes and nebulae, ancient star clusters and newborn suns, distant planets and invisible cosmic forces. And now, as we step back to take in the full picture, we see the Milky Way for what it is: just one among 2 trillion galaxies scattered across the observable universe. A single luminous island adrift in an endless cosmic sea. Within this grand scale, our entire solar system is barely a speck, a microscopic grain of dust orbiting an ordinary star, tucked away in the quiet suburbs of a spiral arm. From here, the vastness of the galaxy stretches in every direction, 100,000 light-years across, filled with hundreds of billions of stars, each with their own worlds, their own possibilities. The distances are so immense that even light, the fastest thing in existence, takes centuries, even millennia, to travel between the stars. Yet somehow, from this tiny vantage point, on this fragile planet, we've managed to glimpse it all. It's easy to feel small in the face of such immensity. But being small doesn't make us insignificant. Every atom in our bodies was forged in the heart of ancient stars. The carbon, oxygen, and iron that make up who we are were born in the fiery deaths of suns that lived and died billions of years before Earth even formed. We are, quite literally, the Milky Way made conscious, fragments of the galaxy that have learned to look back at themselves and ask where they came from. That act of curiosity, of wonder, of exploration, is the galaxy thinking about itself. By studying the Milky Way, we're not just mapping stars or measuring orbits, we're uncovering our own origins. We're learning how the elements that form our oceans, mountains, and cells came to be. We're discovering how our sun and planets fit into a pattern of creation that stretches across billions of years. And as we look outward, we also look inward, realizing that the same forces that shape galaxies have shaped us too. When you stand beneath a dark sky and see the Milky Way arching overhead, you're witnessing the light of stars that may have burned for billions of years before humans ever existed. Some of that light began its journey before the Earth was even formed. You're seeing history, the story of our galaxy written across the heavens. And though the scale is almost beyond comprehension, there's something deeply grounding about it. Because amid all that immensity, this is our home. Our sun, our planet, our species, all of it, belongs to this one beautiful galaxy. We are bound to its gravity, its chemistry, its history. Every revolution the Earth makes around the sun, every orbit the sun takes around the galactic center, is a reminder that we're part of something vast and alive, something that existed long before us and will endure long after we're gone. And yet, even knowing how small we are, we continue to reach outward. We build telescopes to peer into the galaxy's depths. We send spacecraft into the dark, carrying messages for anyone who might find them. We write stories, paint, dream, and wonder. That unending curiosity, that desire to know, is what connects us to the Milky Way more deeply than gravity ever could. So when we gaze up at that silvery band in the night sky, we're not just looking at distant stars, we're looking at our cosmic family, at the place that gave birth to everything we know. The Milky Way is not just where we live, it is what we are. And perhaps that's the greatest discovery of all, that by studying the Milky Way, we're not merely learning about a galaxy, we're discovering ourselves, our origins, our destiny, and our place in the infinite. In the end, the Milky Way is a reminder that while we may be small, we are made of starlight, and that the universe, in all its vastness, is reflected in each and every one of us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.